Hey there, my name is Nikhil, and today I'm going to tell you the hardest way in the world to make $1 million. Our story begins in the year 2000, when the Clay Mathematics Institute released a set of unsolved math questions called the Millennium Prize problems. Now these 7 problems were selected as some of the defining mathematics questions out of the 21st century. The reward for solving any of them? Lifelong mathematic fame and $1 million. The only solved question from this list so far is a Poincare conjecture. Now out of all of these problems, P versus NP is both the most recently discovered and, in my opinion, the simplest to understand. So all that being said, what is P versus NP? And where did it come from? Most of it began with the birth of the modern computer back in the 1960s. Programmers at the time worked really hard to see if these new powerful machines could be used to solve unanswered questions of the past. As programmers eventually figured out through tons of testing, computers weren't good at solving every type of problem. Some problems, like multiplying numbers and sorting information, were simple and didn't take long at all for computers to do. Other types of problems, like the traveling salesman problem and protein folding, were really difficult for computers to solve, and there wasn't really any shortcut or anything that made the process any faster. To find the answer to any of those types of questions, computers basically had to go through a trial and error process and test a bunch of different options and find out which one would work best. As a result of this, programmers created 2 broad categories of problems. Questions that computers could solve easily through a systematic formula were called P-type problems. The ones that couldn't be solved easily and took a lot of computing power were called NP-type problems. One other thing that makes NP-type problems unique from P-type problems is their solutions. It wouldn't be too difficult to check the correct solution to an NP-type problem, but it would take a lot of computing power to find that solution in the first place. Now, as complex as they may seem, most computer scientists actually know what a P-type problem and what an NP-type problem looks like. But the $1 million question that the Clay Mathematics Institute wants to answer to is, does P equal NP? This basically asks if every NP-type problem can be solved like a P-type problem. Something that recently spurred this discussion about whether or not P equals NP are prime numbers. For the longest time, mathematicians believed that the only way to find prime numbers was to repeatedly divide them by other numbers to see if that number really was prime. Because of those repeated calculations, finding prime numbers was thought to be an NP-type problem. However, a recent discovery showed that prime numbers could be in fact found through a systematic process, thus making it a P-type problem. When this news first came out, it was huge. At the time, the general consensus between almost all computer scientists was that if P equals NP can be proven once, then it can be proven over and over again in many other NP problems. Sadly, it turned out that prime numbers were simply misdiagnosed as an NP-type problem, and that they were a P-type problem from the start. But that never stopped people from wondering if there was some connection between P and NP problems. All that being said, it is very hard to see what makes an NP-type problem so much different from a P-type problem. In order to better understand what makes an NP-type problem unique, let's examine one of the most popular NP examples, the traveling salesman problem. So let's imagine that you are a traveling salesperson, selling cameras in cities all across the USA. You don't have a lot of money for gas, so you want to make your route as short as possible while still going through every single city on your list. So, how would you go about solving this problem? Well, as crazy as it sounds, computers actually don't have any big shortcuts to solve a problem like this. They usually just try a bunch of different options to see what will work, hence why it's considered an NP-type problem. Now the traveling salesman problem, as with most other NP type problems, is usually simple to solve in small amounts. This is because the total possible paths between cities can be found by taking the factorial of the number of cities you have. Let's look at an example. If you had 5 cities to travel to, the number of possible arrangements can be found by multiplying 5 times 4 times 3 times 2 times 1, which would give you 120 different paths. Small numbers like this are very simple for computers to simply run through and find the shortest distance. However, when you're working with a bigger number of cities, the number of possible arrangements grows at a staggering exponential rate. With only 20 cities, you already reach a point where there are almost as many arrangements as there are grains of sand in all the Earth's beaches and deserts. If you use 60 cities, there would be a different possible arrangement for every single atom in the observable universe. That is simply a huge amount. The current fastest supercomputer is Tianhe 2, which operates at about 10 to the 15th operations per second. If this computer was set out to fully solve a traveling salesman problem of about 60 cities, it would run for the remaining life of the universe 1 billion times. It is absolutely incredible to wrap your head around problems of this magnitude. There is so much left to be discovered about P versus NP, and we have just begun our research. The person who solves this question will be as great a scientist as Isaac Newton and Albert Einstein. It might even be you. Thank you for watching my video, and I hope you got a chance to learn something out of it.